Alright, so I wanted to make a short video, well, maybe a medium-sized video with some odds and ends we've missed, and I think it's better fit for a little video to add to the class, so here we go. First of all, the mean value property. I'll give you a definition here. So what this definition says is that if we've got a continuous function on a domain, alright, and this disk of radius rho has subdisks of radius r, right, then we can talk about the average value of h of z on a circle of radius r centered at z naught, and it's just defined to be the set of the integral of the set of values z naught plus r e to the I theta. That just takes you around the circle, right? So like a typical point on the circle centered at z naught would be like this point here would be z naught plus r e to the I theta. That would be a parameterization of the circle going around z naught at radius r. And so we add those values up and then divide by the 2 pi. That gives us the average value of h on the circle. Alright, so that's the definition. And so well, here, like I said, it's a parameterized circle, right? And we can argue that a sub r goes to a sub z naught for small values of r, right? As you shrink the circle down to nothing, then you should just be left with z naught, right? So now notice that h of z naught integrated from 0 to 2 pi would be 2 pi h of z naught, so divide by 2 pi, and okay, so anyway, getting to the point here. If we take the difference of a of r minus h of z naught, then we can rewrite that as, here's the definition of a, the average, and then here's that little trick identity I just put there, and then that's less than or equal to the modulus of the difference of these two guys divided by 2 pi, and then by continuity of h, we get that this integrand tends to 0 as r goes to 0, and it follows then that a of r goes to h of z naught as r goes to 0. And then this brings us to the following theorem, excuse me, which says that the average of the values of a harmonic function on a disk is the value of the function at the center of the disk. So here it is. Remember what harmonic means. Harmonic means that it solves Laplace's equation, right? And here it is. Theorem 8.42. If u of z is a harmonic function on a domain D, and if this disk fits inside the domain d naught, then the value of u at the z naught is equal to the average of u around any circle of radius r where r fits inside. Again, the picture here is something like here's your radius rho disk, right? Your center is z naught, and we're calculating the average over some circle based at z naught centered inside the rho disk. All right. And so in that context, the value of the harmonic function at the center point is the average of the harmonic function around the circle. Now the proof I say is given on page 86. I'm of course referring to game 1 there. But here's the proof. We'll look through it here together. So if it's a harmonic, we have this form is closed. Therefore, it's exact because we're dealing with a disk which is simply connected. And so the integral around the loop of this form should be 0. But when we actually calculate the details of this, we get the average. Well, let's just work through it here. So parameterize the circle by x equals to x naught plus r cosine theta, y equals y naught plus r sine theta. There's the real and imaginary components of my previous formula. Talked about a couple minutes ago. And so you calculate dx, you calculate dy, you put them up in here, and out pops this partial u partial y sine theta and partial u partial x cosine theta. The minus with the dx and the minus in the form statement right here, they cancel out, we just get a plus. And then if you look at it, well, that's nothing more than by the chain rule, partial u partial r, right? Because you have the y dependence and the x dependence and how they change with r. So by the multivariate chain rule, this is just partial u partial r. And so, but this, of course, partial u partial r evaluated is z naught plus r e to the I theta. And so if I divide by, let's see here, 2 pi r, well, this is 0, right? So 0 equal to that. Divide by 2 pi r, I get 1 over 2 pi, partial r of that. Then, and here I'm using a theorem of analysis that we ought to prove in the real analysis course, which is that given a certain condition on u, we can commute the integration and the partial differentiation like so. So I can pull the partial derivative out. And after having done that, what are we looking at? Well, we're looking at the average value of u on the circle. And you've just shown, excuse me, shown that that average value is constant, right, as r changes. And so, again, using some analysis there. So we have shown that that this integral is constant for any row between 0, for any r between 0 and rho. And more to the point, since we can let r go to 0, and we've argued before that that gives us u of z naught, it follows that this is equal to u of z naught for each r. And that's the theorem. So more generally, functions which have this property are said to have the mean value property, and here's the property, because it's yet another characterization of a function being complex differentiable. All right, so we say a continuous real valued function h of z on domain D has the mean value property if for each z naught in D, the value of h of z naught is the average of h of z over any small circle centered at z naught. Again, this is the mean value property. And the point of this section is that the harmonic functions have the mean value property. Now, okay, so that was, we're thinking of the harmonic function there as being real valued, but this extends to the complex case. Ooh, but not here. Sorry, I'm thinking of the next section. Next section, actually, so this will not take long, but I should mention this. The theorem is called the strict maximum principle, the real version. Yet another fun fact about harmonic functions. If we have a real valued harmonic function on domain D such that it is bounded above by m, and then if we have the u of z naught is equal to m for some z naught in D, then it follows that the value of the harmonic function is constant and equal to m throughout the domain. Okay, so in other words, if a harmonic function attains its maximum somewhere in a domain, which remember is an open connected set, right? Then that means it has to stay at that maximum the whole time for every point in D. Now this is the proof that I was alluding to earlier in the course that involves the other notion of separation. And I'd be happy to go through it in my office hours in more detail if you'd like to see it. Proof is on Gamelin's page 87. Basically the argument is this. If you look at the set of points S of m, and so that would be the set of points at which the harmonic function attains the value m, you can prove that that set is open. And you can also prove that the set of points for which the function attains a value less than m, you can prove that's also open. But these are disjoint sets, right? And either, I mean, since m is the maximum, either the value is m or it's less than m. So these sets are disjoint and they're open. So these would give you what's called a separation of D. That D is the union of two open sets which are disjoint. But that's not possible because D is connected, and that proves the theorem. So that's a pretty neat place where the connectedness idea comes up. And again, we've defined connected to be path connected, but from a topological perspective, there's a more general notion of connected, which involves just open sets and the notion of a separation. Anyway, more about that in your topology course, if you take it. Anyway, so the other theorem here is the complex analog of the one I just mentioned. And so here it is. If we have a function h of z, which is bounded, complex valued, and harmonic on a domain D, and if we have that the modulus, right, or the absolute value, if you like, of the function is less than or equal to m for all z and d, and if that modulus, or absolute value if you prefer, is attained at z naught for some z naught in D, then h of z is constant. All right. And I won't go through the proof, but it essentially involves some previous things that we've also looked at. There's some really interesting things, like if a function is, let's see here. If a function is real valued and complex differentiable, that forces it to be constant. Because if you look at the Cauchy-Riemann equations being satisfied, that forces the partial derivatives to both be 0, and consequently the function to be constant. It involves that technology here. And then finally, the maximum principle. H of z, a complex valued function on a bounded domain D, such that h of z extends continuously to the boundary of D. If the modulus, or the absolute value of h of z, is less than or equal to m for all z on the boundary, then the absolute value of z is less than or equal to m for all z in D. So, that's actually very, that's an incredible economy of proof, right? That says that if we get a function, right, a complex valued function, and it's harmonic, and we can find a bound for that function on the boundary, right, like this, right, because this, you notice that we're just bounding the function on the boundary, yeah, like that. Then the payoff is that serves as a bound for the whole set. So that's a pretty powerful principle. Again, this means to bound a harmonic function on some domain, it suffices to bound it on the edge of the domain. All right. Again, there's some fine print here because we need what? A continuous extension of that harmonic function to some open set, which is a little bit bigger than D, boundary D, right? And again, Gamelin has more details. Now, the reason I'm going through these things is I think they're important for you to be aware of them. I don't use them too much in this course, but if you were to go on and take a second course in complex analysis, it would be much, much more centered on these ideas, all right? And this is actually the tip of a much larger iceberg, which is that the continuous image of a compact domain attains extreme values. This is, the extreme value theorem. You've seen it in Calculus 1 with the closed interval test, all right? Just, again, to connect with things here. If my domain fits inside some ball, a finite radius, then the real valued function of that domain, and the real valued function of that domain is continuous, then that means that there's going to be some points which the function is maximized and minimized, right? So if the maximum modulus, maximum modulus is a real valued function, yeah, is attained on the interior of D, then the h of D must be equal to the set of that values by our previous result. And so by continuity it extends to the boundary. And so therefore the maximum modulus of h of z is always attained on the boundary given the conditions of the theorem. So that's the maximum principle. And I'm sorry I'm not doing it more justice, but the show must go on here. Now, applications of fluid dynamics, I'll do even less justice to, so let's go on. Sorry. So that brings us to Chapter 9. I've already done suitable damage to the other parts of Chapter 8, so we can go on to Chapter 9 now. The first secret word is juggernaut. All right. Sorry, I'm an idiot. So this is a quote by Gauss that I'm fond of, and most of the quotes that you see in my notes I found in Ramir's wonderful book on complex analysis, which is this fascinating tour de, written by a real master of complex analysis. Anyway, a lot of the things that are beyond Gamelin I've gotten from Ramir's book. But one of those things is this quote from Gauss. And here's what he says in 1811 in a letter to Bessel. Like of Bessel functions, yeah. So he says, what should we make of this integral of phi of x dot dx for x taking a complex value? All right, so if we're to proceed from clearer concepts, we have to assume that as x passes via infinitely small increments, each of the form alpha plus I beta, from that value at which the integral is supposed to be 0 to x equals a plus b, where then all the values are summed up. In this way, the meaning is made precise. The progression of x values can take place infinitely many ways. Just as we think of the realm of all magnitudes as an infinite straight line, so we can envision the realm of all magnitudes, real and imaginary, as an infinite plane, wherein every point which is determined by an abscissa A and an ordinate B represents as well as the magnitude A plus BI. Incidentally, I have at times been told that the concept of a complex plane was later invented by other people in the mid-19th century. This letter is clear evidence that Gauss had a clear understanding that the complex plane had a geometric significance. Here you go. Proof. Anyway, the continuous passage from one value of x to another, A plus BI, accordingly occurs along a curve and is consequently possible infinitely many ways. But I maintain that the integral, computed via two different such passages, always gets the same value, as long as phi of x equals infinity never occurs. Oh no, don't tell your professors Gauss said something was equal to infinity. Oh my goodness, look at this. How dare he. Never occurs in the region, he must not know anything. Sorry, it's Gauss, what am I saying? And the region of the plane enclosed by the curves describing these two passages. This is a very beautiful theorem, whose not so difficult proof I will give when an appropriate occasion comes up. And closely related to other beautiful truths having to do with our developing functions in series. The passage from point to point can always be carried out without touching the one where the function takes an infinite value. However, I demand that those points must be avoided lest the original basic concept of the complex integral, lose its clarity and lead to contradictions. Moreover, it is also clear how a function generated by the integral of a complex valued function could have several values for the same values of x, depending on whether a point where the function takes an infinite value gone around not once, or not at all, once or several times. If, for example, we define the little logarithm of x having gone around x equal to 0 one or more times or not at all, every circuit adds a constant 2 pi I or minus 2 pi I, and thus the fact that every number has multiple logarithms becomes quite clear. Again, this is from a letter Gauss wrote in 1811. It gives you a clear indication that Gauss already had at this point. Now, this will become more clear as we go on in this course, but a pretty clear understanding, in some sense, of many of the major calculations we'll discover and are largely attributed to Cauchy. Or, I guess later, maybe Riemann, perhaps. I don't know. History is not my strong suit, but this is very fascinating, especially if you go back and read this later as we learn more about residue calculus and so forth. But the reason one of your homework problems I've assigned for you, I wanted you to actually kind of try to appreciate this little sentence right here with a homework problem. That's what one of your homework problems is about, is really just exploring this concept that Gauss laid out here in this letter in 1811, that we could define the logarithm, and depending on what path we took, we'd get different values. And that's kind of interesting, and you could think about why that means that we should define the logarithm on a slit complex plane if we want to get a single value. You see, if we're on a slit complex plane, we can't loop round and round the origin. We're stuck at most going, well, not even the whole time around, right? You can only limit the whole time around. All right, so I will move on. Just a little historical tidbit there for you. Now, we went through this proof of Cauchy's integral theorem, I believe, in class, right? And I had some unfortunate error in example 9.33. I'd like to address those at this point. So here we go. So my fix for this example 9.33 was simply to put a 2z in the numerator. Having done that, I think it starts to make sense. So first of all, partial fractions becomes easy because you can just add 0, like z plus I plus z minus I, and after you do that, you can clearly see that the partial fractions decomposition, canceling like this with that, it gives us 1 over, oh, this one, 1 over z minus I, and this with that gives me 1 over z plus I, so that's the partial fractions decomposition of 2z over 1 plus z squared. And then I let gamma epsilon denote a little circle centered at P, right? And the radius is epsilon. And let's see here, what else? Positive orientation, which means counterclockwise. So like that, yeah. Yeah. And you can check a similar calculation to what we did in class, that the integral of dz over z plus I is 2 pi I. Excuse me. And on the other hand, if you integrate over that circle centered at p equals to minus I, then you'll get this here. You get 0 if we do that integral. All right, so apparently, if it's that thing Gauss was just talking about, right? That something special about infinity being in the domain of the integration, right? This takes a value of infinity at z equals minus I in some sense, right? This does not. So, in other words, this dz over z minus I is actually, what's the word? Well, dz over z minus I is actually exact. This is actually an exact form on a circle centered at minus I of a sufficiently small radius. More on that in the next page here. So on the other hand, we have that for the circle centered at I, this form is exact and that form is not exact. It, in fact, it has a non-trivial integral around the loop. All right? You can do these calculations. I encourage you to do it if you don't know how. Especially if you don't know how, you should do it. If you don't know how to get started, ask me, I'll tell you. All right, excuse me. So suppose we got a domain D which includes plus or minus I. All right, so I'll draw that here. So here's your I, here's your minus I. I don't really care what D looks like. All right, and we can let S, basically, we just take circles of radius epsilon, appropriate epsilon, make it small enough so that both circles will fit in, right? So if you make one of the circles epsilon's too big, you make the other ones smaller, right? Make them both smaller. Anyway, so, radius epsilon, we can do this because, again, D is a domain, which means it's open, right? It's got fuzzy edges. So we can find these little circles around I and minus I. And I say let S be D minus the interior of those circles. So basically, you just cut those circles out of D. And what that's going to leave us with, right, is everything except what's inside those circles. Like that. All right? And, okay, so this then is a picture, what's in gray is a picture of S. Okay? Now, the boundary of S is what? It's equal to the boundary of D, right? Unioned with, let's see here, in my current lingo, gamma, curses, I think minus epsilon I, and I want to say my current notation, gamma epsilon minus I. And I got to put the minus because they're both clockwise oriented, because we have to make them oriented so that if you were to imagine yourself walking along the inner circles, S would be on your left, right? So if I do these clockwise, if you imagine yourself a little dude walking along the edge, this S would be on your left if we make these clockwise oriented, right? Okay. So this is the natural orientation of S. Natural in the sense that it makes Green's theorem work. All right? All right, so then, since D is open, all right, getting to the point. F is holomorphic on S, right? Because remember f of z, I'll write the, how did we figure out? It was it 1 over z plus I plus 1 over z minus I, right? So the place where these are misbehaving are at plus or minus I, but those are, plus or minus I. Oops, sorry, I'm off the grid here. Plus or minus I are not an element of S. So F is clearly holomorphic in S because these can be differentiated, all right? Complex differentiated. Let me take the picture away. So we can apply Cauchy's theorem on S, all right, which says that the integral of a holomorphic form around the edge is 0. But this edge of S actually has 3 pieces, the boundary of D, and then the circle and the other circle piece, right? But remember, minus I is not troubling for this, so that just integrates to 0 because that form's exact. And this is not troubling that it integrates to 0 because dz over z plus I is exact on the circle of radius epsilon centered at I. On the other hand, these two guys give us 2 pi I, 2 pi I. So I get minus 2 pi I, so put them on the other side, and there you go. The integral over the boundary of d is 4 pi I. Now, you're like, whoa, 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 which d are you talking about? You never really said what d was. I just said d was some domain which contains these two, right? Yes, that's right. We've just calculated the value of the complex integral around the, the boundary of any such region that just contains plus or minus I, right? So you mean to tell me if d was something weirder, it would still do it? Yes, I could even do things like put a hole in d, right? I could put a hole in d, and then this, 4 pi I just calculated would be the value of the integral of f of z around the outer edge and the inner edge appropriately oriented. The generality of the calculation we just did here, it's hard to overstate. Now, on the other hand, it's fun to think about what this integral looks like in terms of, if I just focus in on, let's focus in here on this one. Excuse me. So I'll focus in right here on this piece right here. And if we do that, we've got that, so if I'm in this circle, centered at minus I, so it would be this circle down here. Sorry, I'll bring it up here for a second. My other picture down here, this circle down here, right? So down here, we could, I say that we can pick a log. Say d log of z minus I. Now I said that down here you could do, later in the paragraph under it, I said that you could choose like log of, I think pi over 2 z minus I. You could use that specific choice of the, we could use this one specifically down here, and that would be okay, right? Because you notice where that doesn't behave is up here, right? This is where it's got the angle jump. And on the other hand, on the upper circle, right, to do this calculation here, I could do, for this circle, right, I have the differential log z plus 1, so I could do like, for example, the other choices, but here's one, log of minus pi over 2, z plus I could be a value I choose for that logarithm, right? It doesn't really matter which one I choose. The point is I can choose one that goes all the way around the circle because I don't, excuse me. This does not hit 0. Z plus I does not hit 0 on that circle, right? And so the logarithm doesn't run into trouble. And I don't have to encircle the origin, right? The point is that this log gets jumped down here. And so that is in fact a potential function for z1 over dz over z plus I, right? So that integrates to 0 and just leaves you the integral of that, which is 2 pi I. Okay, so there's the mechanics of how those can be thought about in terms of explicit antiderivatives, if you will. There's a lot in this example, and if you understand it, it's a good thing. All right, so that brings us to the Cauchy integral formula. All right, and I think I'm going to pause here and get a drink, and then I'll start again.